extreme values of functions on closed intervals. Definition: let f be a function with domain D, then f has an absolute maximum value on D at the point C if f of x less than or equal to f of c for all x in D, and an absolute minimum value on D at C if f of x greater than or equal to f of c for all x in D. So what we have here, f of c is absolute maximum, and here on this part, f of c is absolute minimum. Now here on this part, we have function rule, domain, and absolute extrema on D. For part A, y is equal to x squared. In that case, domain is negative infinite, positive infinite, and here on this part, no absolute maximum, so we don't have absolute maximum, but we have absolute minimum of 0 at x equal to 0. And the next one, y equal to x squared. Here, domain is closed interval 0, 2. So in that case, we have absolute maximum of 4 at x equal to 2. So using this point 2, here we have 2 squared and y is equal to 4. So that is absolute maximum. And absolute minimum is when x is 0. So using 0, here on that part, 0 squared, and the answer for y is 0. So absolute minimum is 0 when x is equal to 0. Next one, y equal to x squared. Now our interval is parentheses 0, 2 bracket. Here in this case, absolute maximum is 4 at x equal to 2. So here again, when we have x equal to 2, 2 squared, y is 4. So that is absolute maximum. But in this case, we don't have absolute minimum. So the difference between B and C is that here we had bracket. So that is closed interval, but here is parentheses. So it's not closed on this part, it's open. Part D, y equal to x squared. Now here interval is 0, 2, but the difference between this one and part B is that here we have open interval, it's not closed. So because of having open interval here in this case, we don't have absolute maximum and we don't have absolute minimum, or we can say no absolute extrema. So here we have a graph for each one of these that we had here on top. For part A, we said absolute minimum of 0 at x equal to 0. So that point is absolute minimum. And for part B, here we have absolute maximum of 4. So that is absolute maximum. And here this point is absolute minimum, which is 0, when x is equal to 0. And for part C, absolute maximum of 4 at x equal to 2. So it's that point. No absolute minimum, because here that point is open circle, it's not closed. We cannot say that that is absolute minimum because it's open circle. And part D, here we had open interval, it's not closed. So we cannot say that that is absolute maximum, and we cannot say that this is absolute minimum. So no max or no mean. We don't have absolute max, we don't have absolute minimum. Theorem 1, the extreme value theorem. If f is continuous on a closed interval a, B, then f attains both an absolute maximum value uppercase M and an absolute minimum value lowercase m in a, B in this closed interval. That is, there are numbers x1 and x2 in this closed interval a, B with f of x1 equal to lowercase m and f of x2 equal to uppercase M, and M is absolute minimum less than equal to f of x, and that is less than equal to M, which is absolute maximum for every other x in this closed interval a, B. On this part, we have maximum and minimum at interior points. So this is max and here is mean. Here on this part, maximum, minimum at end point. So this is maximum and here is minimum. Now this part, minimum at interior point is this point, and maximum at end point. Here we have maximum. Now on this part, maximum at interior point. So this is maximum point, and minimum at end point, and that is minimum. A function f has a local maximum value at a point C within its domain D if f of x less than or equal to f of c for all x belonging to domain lying in some open interval containing C. The function f has a local minimum value at a point C within its domain D if f of x greater than or equal to f of c for all x belongs to D lying in some open interval containing C. So this one, what we have here, that means x belongs to D. Now what we have here on this part is between A and B inclusive. So x is between A and B inclusive, meaning that our interval is closed interval. We have bracket A, comma B bracket. So what we have here, this point, that is absolute minimum, because there is no smaller value of f. Anywhere also a local minimum, so this one is local minimum, but at the same time it is absolute minimum. This one is local minimum, it's not absolute minimum. Here again, this is local minimum, it's not absolute minimum. Here is absolute max, so that is absolute maximum, no greater value of f anywhere. Also, this point is also a local maximum, and here this point is local maximum. So here on this part, the smallest value that you can find for f is this point. That's why this is absolute minimum. And the largest value that you can find based on this graph for f is this point. So that's why this is absolute maximum. Turn to the first derivative theorem for local extreme values. If f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, then f prime of C is equal to 0. Now what we have here on this part based on this graph, local maximum value is this point when x is equal to C. The slope of this line is equal to 0. The slope of these secant lines here on left side is greater than or equal to 0, and the slope of secant lines here on right side is less than or equal to 0. Now here we have definition: an interior point of the domain of a function f where f prime is 0 or undefined is a critical point of f. Find the absolute extrema of a continuous function f on a finite closed interval. So here we have steps. Step 1, find all critical points of f on the interval. Step 2, evaluate f at all critical points and endpoints. And step 3, take the largest and smallest of these values. Examples: find the absolute maximum and minimum values of the following function on the given interval, then graph the function. Here I have this graph, so I'm going to find absolute maximum and minimum values. F of x is equal to 8 divided by 9 times x plus 1. Here we have closed interval. X is between 0 to inclusive. So we have to find critical points first. In that case, we have to find f prime of x. And this is equal to 8 divided by 9. Now next step is solving for x. So in this case, we don't have x. That means that if I try to solve this one for x, I'm not going to have critical points. But the point is, we have to follow steps. F prime of x equal to 0. But in this case, we have 8 divided by 9. And that is not equal to 0. So this means there is no critical points. Next step, we have to evaluate f at critical point and endpoint. So in this case, we don't have critical points. And now we have to use endpoints 0, 2, and evaluate f. So what we have here, when x is 0, f of x is 1. When x is 2, f of x is 25 divided by 9. And the largest number that we can find between these two numbers, between 1 and 25 over 9, this point is the largest number. So that is absolute maximum. So we have absolute maximum value 25 over 9 when x is equal to 2. And the absolute minimum is 1 at x equal to 0. So this graph is based on what we did here on this part. When x is 0, y is 1, so it's this point, and that is absolute minimum. When x is 2, y is 25 over 9, which is that point, and that is absolute maximum. After finding these 2 points, we can draw a straight line to connect 2 points that we have. Find the absolute maximum and minimum values of the following function on the given interval, then graph the function. G of x is equal to 2 secant x, and our closed interval is negative pi divided by 3 less than equal to x less than equal to pi divided by 3. First step is to find critical points, and we have to find g prime of x first. That is equal to 2 secant x tangent x. Instead of secant, we can use 1 over cosine, and for tangent, we can use sine over cosine. So what we have here, g prime of x equal to 0, 2 secant tangent equal to 0. We have 2 times 1 over cosine times sine over cosine equal to 0. So what we have here on this part, multiply 2 times 1 times sine. On top we have 2 sine x, and denominator we have cosine times cosine, so that is cosine squared. So this one equal to 0. To solve what we have here, set the numerator equal to 0 and solve for x over this given interval. So what we have here, based on what I have in numerator, 2 sine x equal to 0, solving for x, x is 0. Now to find values of x where g prime of x is undefined, so using this one, set the denominator, which is cosine squared, equal to 0 and solve. So cosine squared equal to 0. Solving for x, x is equal to negative pi divided by 2 and pi divided by 2. But the point is, our interval is negative pi over 3 and pi over 3. So this is closed interval, and what we have here on this part, we have negative pi divided by 2 and pi divided by 2. So these are not in the given interval, meaning that the only critical point that we have is on that part, x equal to 0. So we only have one critical point, at x equal to 0. So we're not going to use these two to evaluate g of x. So here on this part, evaluate g of x at the critical point x equal to 0. So g of 0 is equal to 2. So we have 2 times secant 0, and secant 0 is 1. So 1 times 2, the answer is 2. Now evaluate g of x at endpoints. Our interval was, closed interval is negative pi over 3, comma pi over 3. So here I have negative pi over 3. Finding g of negative pi over 3, that is equal to 2 times secant negative pi over 3. So here we have 2 times 2. So secant negative pi over 3 is equal to 2. Remember that secant is 1 over cosine, and cosine negative pi over 3 is equal to 1 over 2. So 1 divided by 1 over 2, that is equal to 2. So here is what we have for secant. So we have 2 times 2, and that is 4. Now here finding g of pi over 3, that is equal to 2 times secant pi over 3, and secant pi over 3 is equal to 2. So it's 2 times 2, the answer is 4. Now what we have after evaluating g of x, the smallest value that you can find is 2, so this is absolute minimum. So absolute minimum value is 2 at x equal to 0. And absolute maximum value is 4 at x equal to negative pi over 3 and pi over 3. So here we have 4, and here again we have 4. So this part, absolute minimum, and here we have absolute maximum. So based on the points that we have for absolute minimum and absolute maximum, here is our graph. So this point is absolute minimum when x is equal to 0. G of x is 2. And here these 2 points, we have absolute maximum when x is negative pi over 3. G of x is 4. And when x is pi over 3, g of x is 4. So this is our graph. Now here on this part, using this graphing calculator, here we have 2 secant x, and what we need based on our closed interval is this part of graph. Based on what we have here, this point 0, 2, that is absolute minimum. And here we have absolute maximum as negative pi over 3, 4, and pi over 3, 4. So these 2 points are our absolute maximum. Find the absolute maximum and minimum values of the following function and the given interval. F of x equal to x squared minus 4, x is between negative 2, positive 3 inclusive. So first we have to find critical point, and that means we have to find f prime of x. So critical point of f is interior point of the domain of a function f, where f prime is 0 or undefined. So first step, here finding f prime of x, that is 2x, then we should have f prime of x equal to 0. So here we have 2x, that is 0, solving for x is 0. Here after finding f prime, we don't have variable in denominator, so denominator is 1, meaning that In this case, f prime of x is not undefined. Next step, we have to evaluate f of x for critical point and endpoints. So f of 0 is equal to -4. That is for critical point. And for endpoints, we have f of -2 is equal to 0 and f of +3 that is equal to 5. Now compare all these values that we have for f of x. The smallest that we can find is -4, so that is absolute minimum. And the largest number that we can find is 5, so this is absolute maximum. So based on these 3 points, we have this graph. Here this point is -2, 0. Here on this part we have absolute minimum, and that is 0, -4. And here on top we have absolute maximum, and that is 3, 5. Note that when you're trying to graph what we have here, this point and this point, these are end points. So finally connect all these 3 to graph this function. Find the absolute maximum minimum values of the following function on the given interval, then graph the function. G of x is square root of 16 minus x squared. X is between -4, +3 inclusive. So first I'm going to find critical points. And here endpoints are -4, +3. The next step is evaluating our function based on what we have for critical points and endpoints. Here we have this graph based on what we're going to have for absolute maximum minimum. So here g of x is 16 minus x squared. I'm using exponent, so this is 1/2. That is our power. Now finding g prime, that is equal to 1/2 times 16 minus x squared. Power is 1/2 minus 1, so this is -1/2 times. Now derivative of what we have inside, so that is -2x. So this will multiply by -2x. Now we can simplify. So 2 divided by 2. G prime of x is equal to -x times 16 minus x squared. Power is -1/2. So g prime is equal to -x divided by square root of 16 minus x squared. So this is what we have for g prime. Now we have to find where g prime is 0 and where it is undefined. So g prime of x is equal to 0 when numerator is 0. So what we're going to have for that part is that x is 0. And then for g prime of x, when it's undefined, we have to use what we have in denominator. So g prime of x is undefined where the denominator equals to 0. So here denominator equal to 0, and in that case x is -4. We have to see what we have for our domain. Domain is -4, +3, so our interval is -4, +3. That's why I can only use -4. I cannot use +4 because +4 is not in this interval. So these are what we have for critical point, and now we have to evaluate our function based on critical point and endpoints. I'm going to find g of 0, that is square root of 16 minus 0 squared, that is 4. And here we have critical point, we have -4, but the point is that our endpoint is same number, that is -4. So next step, finding g of -4 and g of +3. So what we have for g of -4 is the square root of 16 minus -4 squared, so that is equal to 0. And g of +3 is equal to square root of 7. Now we have to find absolute maximum, absolute minimum based on what we have here. So the smallest number that we have is 0, so that is absolute minimum. And the largest number that we have here on this part is +4, so that is absolute maximum. So here on this part we have the graph for square root of 16 minus x squared. And our domain is -4, +3. So it's between these two vertical lines. And the absolute maximum that we have here on this part is 0, 4. Absolute minimum that we have on this part based on what our domain is -4, 0. So I don't have this part of graph for square root of 16 minus x squared because of our domain. Here we have x between -4, +3 inclusive. Now here on this part, find critical point. Y is equal to x cubed plus 3 times x squared minus 144 times x plus 7. So we have to find y prime, or derivative of y with respect to x. So this is equal to 3x squared plus 6x minus 144. Now to find critical point of y, we have to use this derivative and determine where the derivative is 0 or undefined. So what we have here on this part, this is a polynomial and it is defined for all real numbers. So what we have to do to find critical point, use this polynomial equal to 0 and solve for x. So here we can factor 3. So we have 3 times x squared plus 2x minus 48 factor. So here we have 3 times x minus 6 times x plus 8 equal to 0. Now solving for x, here x minus 6 equal to 0, x is 6, or x plus 8 equal to 0, x is -8. So the critical points are at x equal to 6 or x equal to -8. Find the critical point, domain endpoint, and local extreme values for the function y equal to 2x times square root of 144 minus x squared. The critical point is interior point of the domain of function f, where f prime of x is 0 or undefined. So first we have to find domain of our function. Because of having square root, what we have inside 144 minus x squared, that part should be greater than or equal to 0. And then solve for x, x is -12, +12, so the domain is closed interval, -12, +12. Now to find critical point, we have to differentiate the function with respect to x. and this is equal to this part 2x times derivative of what we have after, so derivative of square root plus this part over square root times derivative of 2x. So this is equal to 2x times derivative of square root. Here is negative x divided by square root 144 minus x squared, and then plus square root of 144 minus x squared derivative of 2x. Here is 2. Now we have to simplify. This derivative is undefined when the denominator of the first term is 0. So it is undefined when x is negative 12 and x is positive 12 based on what we have here on this part in our denominator. These are same points that we have for our domain. So these values are the domain endpoints. The derivative is always undefined at domain endpoints because there is only a one-sided limit, while the derivative requires a two-sided limit. Since critical points must be in the interior of the domain, there are no critical points where the derivative is undefined. But we can find critical points where the derivative is 0. So this derivative is equal to 0, solving for x. Here we have denominator square root of 144 minus x squared. Now we can simplify what we have in numerator. Here, multiply these two, we're going to have 144 minus x squared. And here on this part we can cancel. So what we're going to have is negative 2 x squared plus 2 times 144 minus x squared equal to 0. Now we simplify this part, we're going to have 2x squared equal to 144. So x squared is equal to 72. Now solving for x is negative positive square root of 72. So that is negative positive square root of 9 times 8. So the answer is negative positive 6 times square root of 2. So here is what we have for x. Now finding local extrema of the function. So local extrema only occur at the endpoints of the domain or at critical points. So let y equal to f of x, and now we have to evaluate our function based on what we have for critical points and endpoints. So what I have for f of negative 12 is 2 times negative 12 times square root of 144 minus negative 12 squared. So the answer for this part is 0. For f of positive 12, we have 0. For f of negative 6, square root of 2, the answer is negative 144. And here, f of 6 times square root of 2, we have positive 144. So we have all these 4 points based on what we had for critical point and endpoints based on what we have for our graph. Negative 6 square root of 2, comma, negative 144, which is this point. That is local minima, and negative 12, comma, 0. This is local maximum. 12, comma, 0, this is local minimum. And this point here on top, 6 square root of 2, comma, 144, this is local maximum. So again, these 2 points, negative 6 square root of 2, comma, 144, and 12, comma, 0 are local minimum, and 6 square root of 2, comma 144, and negative 12, comma 0 are local maxima. Find critical points, domain endpoint, and local extreme values for the function. So here on this part, we have to find domain first. So for the first piece of the function, here domain is negative infinite, comma 2. And here on this part, our domain is 2, comma infinite. So note that here on this part we have bracket because here we have equal to. So what this means, the domain of piecewise function is negative infinite, positive infinite. So here in this case, the domain of function is defined for all real numbers. What that means, there's no domain endpoint where there. So here on this part, the domain of the function is defined for all real numbers. So that means there are no domain endpoints where there could be an extreme value. So now we have to find the derivative of each and critical point. So first find y prime for each piece of function. So here we have y equal to negative x squared minus 3x plus 9. Finding y prime for the split, that is negative 2x minus 3. And for the second part, here we have negative x squared plus 5x minus 7. And y prime is negative 2x plus 5. Here is what we have for y prime, negative 2x minus 3 for when x is less than 2, and negative 2x plus 5 for x greater than 2. I don't have x equal to 2 here on this part because we have to find limit as x approaches 2 from the left and limit as x approaches 2 from right. If those two were equal, in that case we're going to say y prime is defined at x equal to 2. So here finding limit of y prime as x approaches 2 from the left, we have to use negative 2x minus 3 for when x is less than 2, and the answer for this part is negative 7. Limit of y prime as x approaches 2 from right, using this negative 2x plus 5 when x is greater than 2, and the answer for that part is 1. So we don't have same answer. We have negative 7, we have positive 1. What this means, y prime is undefined at x equal to 2. Therefore, the critical point where y prime is undefined is at x equal to 2. Now we have to find where y prime is 0. So the first piece is negative 2x minus 3 equal to 0, and the second piece is negative 2x plus 5 equal to 0. Solving for x here, x is negative 3 over 2, and here on this part we have 5 over 2. So both of these points are within their domain. What that means, the critical points where y prime is 0 are at x equal to negative 3 over 2 and at x equal to 5 over 2. Now we have to evaluate y at the critical points negative 3 over 2, 5 over 2, and 2. So we have to use based on what we have here, negative x squared minus 3x plus 9, use that one for when x is equal to 2 and x is equal to negative 3 over 2. And use negative x squared plus 5x minus 7 for when x is greater than 2, and what we had for x in that case was 5 over 2. So here on this part we have first piece, and I'm going to use negative 3 over 2 for x. So the answer that we have here, y is 45/4. Now on this part, for second piece, here our x was 5/2. And our answer for y is -3/4. Now here we have x equal to 2. And the answer that we have for y is -1. So using graphing calculator based on the first and second piece, here -1.5, 11.25, or -3/2, 45/4, that is local maximum, and 2.5, -0.75, or 5/2, -3/4, that is local maximum, and we have 2, -1, this is local minimum. So this is our graph here. So this point here on top, that is local maximum. Here on this part we have local maximum, and here this point is local minimum.